Hello all, welcome back to our tutorials on high-speed designs. In the previous video we have seen some of the properties which might cause the signal to get degraded. These we have called as characteristics of the transmission line. So we'll talk about one of the important characteristic, which is called a characteristic impedance. So characteristic impedance, basically if you see the image here, there is a source and a destination, and the two lines between them can be called a transmission line. So when there is a signal that is being forwarded from source to the destination, if we take any specific point of time, at that point of time and at that instant, the ratio of voltage to current gives the characteristic impedance. That's a simple definition of a characteristic impedance. So this characteristic impedance basically is labeled as Z0. So Z0 is the characteristic impedance, which is one of the major parameter in our designs. So this is what need to be considered if you need to have a decent output in high-speed designs. So moving to the next point, one of the other important point which we have to remember here is basically which most of the people might have studied in academics, which is called the maximum power transfer theorem. So basically what does maximum power transfer theorem state is, when there is a source which is providing some output and it goes to the load, the power that is being transmitted by the source, if this entire power need to be absorbed by the load without any losses, then the condition that need to be met is the impedance of the source must match with the impedance of the load. That means there should be a common impedance across from the source to the load. So this condition which we are saying is called the maximum power transfer theorem, which we have studied in academics. So this basically, as we talk here, deals more with the impedance of the transmission line. So this is a very important aspect in high speed designs, which the designers have to keep an eye on, and the entire analysis that we do on high speed signals, the simulations and all, revolves majorly around this point. And then while we talk about the maximum power, characteristic impedance and all, let us talk about the types of transmission lines involved. So as we said previously, the wires that are being laid over, example a coaxial cable which carries a cable signal, is an example of a transmission line. And then a twisted pair, like example which we use in our household applications, is also an example of a transmission line. And then waveguides is another example. And then optical fiber is another example of transmission line, and the PCB trace. So as we said, the PCB traces are treated as the transmission lines above certain frequencies. So they also come under transmission lines. So even though we talk about transmission line as a ghost here, transmission line is just a simple medium for helping the signals to travel from source to the destination. So that's the simple definition, and there are several transmission lines, as we said here, which are used for transmitting those signals. So everyone has their own properties, and then based on the type of signals that are being transmitted, based on the type of medium that is present around that area, the transmission line, type of transmission line need to be used. On the same transmission line thing, we are saying that PCB trace is also a transmission line. So these PCB traces could be different types again. So the first thing is called a stripline. So what a stripline is, basically, if you see, if you assume a PCB So if you are already experienced in PCB, we are just giving a view. There will be number of layers, right? 1, 2, 3, 4 or 6 or 2 or 4 or 6 or 8, whatever, depending on your complexity. You can go up to a number of layers. So now here, in this particular scenario, a stripline, if you see the first image here, the PCB trace in between is embedded between two reference planes. So when we say reference planes, the top plane could be a ground or a power, bottom plane could be a ground or a power. So such a PCB trace which is embedded, that means if you have a example 4-layer transmission line, the second layer or the third layer routing is called a strip line, because it is embedded inside the PCB and it is not visible outside. And then the second on the same strip line, there is one more version called differential strip line, so which you see on the fourth image here. So differential strip line is nothing but two signals shall be present, one positive and one negative. So instead of single-ended, it's basically a differential which involves, as we said, positive and negative, and embedded inside the PCB. That means inner layer. And then the microstrip is a normal top level or the bottom level routing that we see on the PCB. So this is a microstrip line. And then similar to differential strip line, there is also differential microstrip line. So here it should be microstrip line, sorry. So that means a differential routing. So we will talk about differential routing in high-speed designs further. This is just an introduction. We know that if we are transmitting signals from source to destination, a single line can be laid with a reference plane, whereas the same signal or any other different signals can be routed over two lines which are complementary to each other, which is called a differential line, which we will introduce in the next videos as a part of these high-speed designs. And differential lines play a crucial role. And then the last one is the dual strip line. So dual strip line meant instead of one strip line, if you see the first image here, there is only one strip line embedded, and then there are two reference planes to that. Now instead of one strip line, there will be two strip lines. So that means it is a dual strip line routing. So there are several other PCB routing topologies, but here we just wanted to restrict to commonly used strip line and microstrip line technologies as a part of the transmission line. So hope we just gave a view of this. And then each of the strip line and microstrip lines have their properties, based on which the impedance of that particular traces shall be decided. So first, if we go to the properties of a microstrip line, so as you see here, this is how a microstrip line looks like, where there is a routing on the top layer and then there is a reference plane. In between, this is a dielectric. Dielectric is nothing but an insulator which is used in PCBs to separate layers. Example, if you have a 4-layer, to separate each and every layer, there is a dielectric in between, so that there is, the signal doesn't flow between the layers. So the impedance of this particular microstrip line depends on several properties. It is the dielectric constant. So dielectric constant of this particular piece material. Whatever the PCB material that we use, the green one we see here, that dielectric constant, and then thickness of the dielectric constant, and then width of the trace, so the top trace which we are routing, and then height of the trace. So all these determine the characteristic impedance of this particular trace or a microstrip line that we are seeing here. So this is the formula that is used. So you can see here, H is the height of the dielectric, this is the height of the dielectric, and then conductor width. Conductor is nothing but the microstrip line which we have routed on the top, you see here, and then conductor thickness. So again, it's a design requirement where you vary the thickness of the conductor. So this is about the microstrip line. Similarly for stripline, again, the properties, the characteristic impedance property of this stripline again depends on the similar characteristics, dielectric constant of that PCB material, thickness of that dielectric, and then width of the trace, height of the trace. The only change is how impedance is going to vary when we route the signals as a stripline and microstripline. So if you keenly observe this, there is definitely a difference in the formula. So there are several tools available over internet where you can use them to directly calculate the characteristic impedance rather than using this formula to determine the impedance. So these two formulas are very important in any of the designs, whether it be low speed or whether it be high speed, and this can be used to determine the impedance and further improve our design, and also simulate and do the required changes to the design based on these characteristic impedance. We will talk in detail about the other points in the next videos. Please let us know if you have any questions. Please post your comments and suggestions, and if you are looking for any additional data, please let us know. Please like and subscribe our channel. Thank you.